So if we put together our idea about infinite limits, aka vertical asymptotes, and limits at infinity, which are horizontal asymptotes, we can come up with a new theorem. So let me just put that in here. These are vertical asymptotes. These are horizontal asymptotes. All right, so we're going to look at this particular problem. We want to consider this function right here, g of x equals negative 2x cubed plus 94x squared plus 245x plus 1. And we want to consider the function's limits at infinity and verify our predictions with the graphing utility. So you'll notice that this is an odd function, right? Because that's an odd degree function. So if you recall from algebra or calculus, this is third degree, that's second degree, first degree, and 0th degree, aka a constant. So the third degree is the most powerful. And since the largest degree is going to win as x goes to infinity, then this will be our champion. This will be the one that will triumph over the other ones. So let me prove this. So let me take the limit as x goes to infinity of g of x. That would be the limit as x goes to infinity of negative 2x cubed plus 94x squared plus 245x plus 1. Now, the highest degree is right here. So since it has the largest degree for a term, it will win. And that means this function, as x goes to infinity, will be heading to negative 2 times infinity cubed, aka negative infinity. So I would posit that this limit will be negative infinity. And I circled it in pen, so you know I must mean business. All right, by the same token, if I let x go to negative infinity, of g of x, of this same function, then that would be the same term is going to win. Oops, 245x plus 1. So if this term wins, oh, and where did I get the negative infinity from? I got that from negative 2 times infinity cubed, which would be negative infinity, right? That's where that's coming from. This one, again, largest degree term, so it's going to be heading to largest degree term. So it wins again. And that means you're heading to negative 2 times negative infinity cubed. But negative infinity cubed is negative infinity, and a negative 2 times a negative infinity is positive infinity. So I would argue this one's going to be positive infinity. Now, let's verify whether I am correct using a graphing utility. So I'm going to graph this function. Well, I've already graphed it, to be honest. That's what Desmos is for. So let me pull up my class materials page. Let me grab this example. And here it is. So here's the function g of x. Oops, sorry, it's a little off screen. So here's the function g of x is equal to negative 2x cubed plus 94x squared, yada, yada, yada. And you can see my scale has got to be huge because this is quite a high degree polynomial. So let me draw a graph of it. And then you can see that I was indeed correct, that as x goes to infinity, which is over here, I'm heading off to negative infinity, right? But as x goes to negative infinity, I'm heading to positive infinity. So indeed, I was correct. All right, so let me flip back to the camera so you can see it. So I've drawn a little picture, and I have to put in a scale just so I have a clue of what I was looking at. So this was, I think, 60,000. Let me double check myself. 60,000, negative 20,000, negative 40, and 60. So let me put those in on my paper, and then I'll show you in just a second. So negative 20,000 and 60,000. All right. So back on my paper, there they are. There's my scale, just to give me a sense of what I was doing. I mean, I know it's not perfect, but you're just trying to give it, you know, a little bit of a sense of what's happening here. So let me show the green one is as we move to the left from the previous page. So I'll try to stick with that. So as we moved to the left, that was right here. That was our negative infinity. That's this portion right up there. And then, yes, it is green. I know it doesn't look like it, but it is, I promise. And then as we move to the right, that was our orange one. So that's this one right here. So you can see it's right there. And that leads us to a new theorem, which is down here, which is saying if you have a polynomial. Now, polynomials are terms of, there's something that's learned and defined in pre-calculus class, but essentially it's a sum of terms where there's nothing but constants and variables to powers, and that's it. There's no transcendental functions, no sine, no cosine, no tangent, none of that stuff. Right? So it's just constants, and then those subscripts, don't freak out about that. That just means that, this is the nth term, this is the n minus 1th term, and so on, down to a sub 0, which is a constant because x would be the 0 power on that one. Right? And then a sub n is called the leading coefficient, and it cannot be 0, because if it was 0, then that wouldn't actually be the leading term. All right, so if we have a polynomial like this, then the limit as x goes to infinity or negative infinity of x to the n will always be infinity if n is even. Let's think about that for just a second. If n is even and n is your leading term, then that's going to mean that if it's positive infinity, it's infinity to the even number. Negative infinity is negative infinity to the even number. And anything to an even power will become positive. So let me just make a couple notes right here. This is the largest degree term, so it's going to determine whether we are heading to positive or negative infinity. So largest degree term determines limits at infinity, either the plus infinity or the minus infinity, either one. In other words, it wins. This is the winner, right? The rest of them you can ignore in a polynomial. All right, now the one I was just giving you an example of right here, so let me throw in a quick little example. If you took the limit as x goes to negative infinity of x to the 4th, that would be negative infinity to the 4th, which, lo and behold, is positive infinity. That's what this is saying. Right? That it doesn't matter if it's even or if the power is even, it doesn't matter if it's positive or negative infinity, you're going to infinity. All right, for number 2, it's saying, let's see here, if the limit as x goes to infinity of x to the n is infinity, and the limit of as x goes to negative infinity of x to the n is negative infinity when x is odd, or when n is odd, So that's saying if you have an odd power, like a third power, let me just give you an example here. So if I had the third power, limit as x goes to infinity of x to, that's an infinity, x to the 5th, that would be infinity to the 5th, and that would be infinity. By the same token, the limit, I'm just trying to separate these, the limit as x goes to negative infinity of x to the 5th would be negative infinity to the 5th, which is negative infinity, right? So they're saying if you go to positive infinity, you're going to be positive, negative infinity, you're going to be negative. That happens when you have an odd power as your leading term degree. All right, then this one, my favorite, we've actually already used this a little bit, which is that if you have a constant like 1 and you divide it amongst infinity to the n power, so you're taking 1, you're dividing it by infinity to the n or negative infinity to the n. It kind of doesn't make any difference. You will always, always have 0. So let me write that one up real quickly. So let me give you an example. If you have, and to be honest with you, it doesn't have to just be 1. That's kind of the argument that we're making out down here, but it could actually be any value, like 5 or 7, any constant. But if you're taking the limit as x goes to negative infinity, I'll throw a negative in there, of 1 over x to the 5th. That would be 1 over negative infinity to the 5th, which is 1 over negative infinity, which is 0. You have 1 or negative 1, you divide it amongst infinity, and everybody gets nothing. That's what this is saying. So, and it doesn't matter if it's positive or negative, and honestly, it doesn't matter if it's 1. This is actually true even if it's just a constant up on top. All right, I'll make a little note of that. Constant k over x to the n, where k is a constant, right? So if you take any real number and you take the limit as x goes to plus or minus infinity on that number, then it doesn't make any difference what that constant is. Once you take the constant and divide it amongst x or infinity or negative infinity, you're going to have 0, right? Because whatever the constant k is, it can't win out over infinity. All right, last but not least, the limit as x goes to infinity or negative infinity of a polynomial p of x is equal to, right, this is what I was saying to begin with. This is saying that the first term is the winner. So that's what this is saying. It depends on the degree of the polynomial and the sign of the leading coefficient. So in other words, the first term, the leading term, I should say, when I say first, I'm implying leading because I'm implying that this is in order, the algebra order of going with the largest degree term first. But let me just put it this way, leading term, right? The leading term, aka the largest degree term, is the winner, and it will determine whether the limit is positive or negative infinity. All right, there we go for that. And that's the answer to this question. So the answer is the leading term. That is what we pay attention to, right? The leading coefficient term. So, well, the leading term and its coefficient. So in other words, the term of highest degree. So the term of highest degree is the most important to us for determining whether or not the function is heading towards plus or minus infinity as we go to infinity, or actually going to 3 as we go to infinity. It's that first degree term, or the leading degree term, that is the most important. One other thing to note really quickly, I'm kind of playing fast and loose with some things here, so let me just make a real quick note. I'm just going to add it in down here. So note. If you think about number 3 for a second and what I was saying, I'm saying that if you take the limit as x goes to, I don't know, negative infinity of, 3 over x to the 5th or something like that, then that would be 3 over negative infinity to the 5th, which is 3 over negative infinity, which is 0, right? So what we're learning is that 3 over infinity is 0. And we earlier learned in section 2.4, just recall this, that 3 over 0 is infinity or minus infinity. It depends on how this function works, right? So was this function positive and going to 0? Was it negative and going to 0? But it was one of these two, right? But we still don't know infinity or infinity and 0 over 0. So we still don't know infinity over infinity, or especially 0 over 0. Those are called indeterminate forms. They could be infinity, they could be 0, they could be 3, they could be 1, they could be any one of those things. So they're called indeterminate forms. We don't know how either one of them is determined to work. As a matter of fact, there is no determination. That's why they're indeterminate. They could be anything. So we just kind of ignore those. We learn how to deal with those in Calculus 2 and Calculus 3. But in general, in Calculus 1, we don't deal with them. Unless we can finagle it so that it's neither one of those. We'll learn some tricks for that. But 0 over 0, infinity over infinity, we don't have good answers for.